Okay, everyone, welcome to Lecture 5. Just a reminder that I hope everyone's on Piazza. We're sending out all kinds of announcements and stuff on there, and you are responsible for knowing those things. In particular, on the Homework 2 post, we're going to constantly be editing it with Q&A and clarifications. So make sure you're checking that Homework 2 post if you have any questions, because there might already be answered in there. In particular, on the solid blocks problem, there's a clarification on there, so you might want to check that out if you haven't already. Other than that, are there any questions before we start with more dynamic programming? A lot more dynamic programming. Okay, so this is basically a list of all the problems I want to talk about. We're not going to go through all the textbook problems, so in particular, at a distance, I might cover, but if not, definitely check it out in the textbook. There's also the subset sum dynamic program. So these are in the textbook that I won't be covering. I try to pick very practical problems to cover today, because I think they're more easy to visualize and tangibly think about. So that's our plan. And one thing that's really important about dynamic programming is this idea called optimal substructure. I'll try to talk about this in every single example, but if you don't hear me say this phrase, feel free to shout out and be like, what's the optimal substructure? And I'll let you know, because it's very important. This is the idea I kind of hinted at a couple lectures ago, which was, if you think about a shortest path in a graph from some node S to some other node T, well, any path in a graph has to start with an edge, right? So if that's the starting edge, and this is the optimal way to get from T to V, so this is optimal, then this entire thing, if the entire thing is optimal, then that one must also be optimal. So the idea here is, suppose the recursion fairy told you that this was the optimal path, but you could hypothetically get an even better path by not using that subpath. Well, you could never do that, because if the recursion fairy could shrink the solution for a subproblem, it also results in a faster path overall. So if you think about it, if you had a shorter path for a part of your drive, well, that leads to a shorter drive overall. So basically, the subproblems are connected. Subproblem optimality leads to total optimality. And I always like to think about the road example, because it's really intuitively clear. If you can improve your time in even a portion of your drive, well, that's going to improve your time overall. It would never make sense for you to do a really long portion at the end, because it's not really helping you. So that's the idea behind optimal substructure, but we'll talk about it extensively. So the first problem we're going to talk about is about minimizing white space in a paragraph. So quite literally, every time you use Microsoft Word, it's doing almost exactly the algorithm we're going to come up with. So if you have a paragraph, it has some fixed end of the line. So we'll call capital L the end of the line. This is the end. And once you pick an end of the line, and you pick the words to go on the end of the line, well, now you can figure out what space goes between each word. So for example, consider this paragraph here. We decided on the first line to pack all those words in there, and so we get few spaces, very short spaces in between. But because of that, we have to have this massive space in the middle here. So this is a consequence of having to fit everything in and kind of you're basically justifying it so that the left word's touching the left margin, the right word is touching the right margin. But instead, you could have done something like this. So instead of packing everything on the top line, you sacrifice some white space on the top, on the first line, so that the second line isn't as bad. Okay? Now, just aesthetically, we probably feel like the first one's really bad. You wouldn't want to read that in some book. So we're going to quantify the badness of spaces by this idea called slop. And so the slop is quite literally, you take the lengths of all the words on a line, and you're going to compare that with the remaining white space. And if there's a lot of white space left on the line, you're going to cube that, and that gives you your total slop. So intuitively, if you looked at this picture here, for the second line, the slop is going to be massive because the lengths of your words are very small compared to the total length of the line, and so you need a large amount of space. So if you think of the number of positions where you're putting a space and cubing that, that's your slop. You're taking that and cubing it. So we're just penalizing lots of white space on a single line. And this is just a specific formula that people use for whatever reason. Okay, so is the problem statement clear? We're given a bunch of words, W1 through WN, and we're given their lengths, L1 through LN, in an array. And our goal is to choose the line breaks between the words so that the total slop is minimized. That's our goal. So let's look at an example. This example again. So this is another great example of why greedy algorithms never work. So this is actually the result of a greedy algorithm. So you might think to minimize white space, you want to pack as many words as possible on a single line. It makes sense. That will be optimal for a single line. So for that single line on top, it's almost completely normal white space. You wouldn't even notice that it's slightly bigger than usual. But the consequence of using this greedy algorithm is that for future lines, they have to have really bad white space. So although you've optimized the first line, the other lines get hurt badly. On the other hand, if we sacrificed a little bit for the first line, we end up getting a better overall looking paragraph. So the total badness for the second paragraph is going to be much less than the badness of the first one. So this is why we need to use DP instead of, say, a greedy algorithm. Because a greedy algorithm would never allow us to sacrifice the first line to improve the rest of the lines. Okay, so any questions so far about what we want to accomplish in this problem? Today you are Microsoft, and we're programming Microsoft Word, basically. Okay? So as usual, let's imagine we're in the middle of our process. So we have some paragraph. And let's say we've already done line breaks for all the top ones. So all of these we've already chosen line breaks for. And we're currently at line I. Or to be precise, we're at word I. So this isn't a line, this is word I. and we want to choose the line break or do something with word I. And here is word I minus 1. Okay? So we're in the middle of the process, and now we want to do something with the ith word. So what kind of decisions might we make involving word I? Think of longest increasing subsequence. So you could put a line break immediately, but you're going to have a lot of white space if you do that. Potentially. So maybe we want to think about what's the next line break. That could be our decision question. Find the next line break. So this is kind of similar to text segmentation, where our goal was to find the next word. We were inserting spaces. Now we're going to be inserting lines. So it's very similar to that previous example. Okay, so our goal is to basically find what J should be at the end of this line. And we want to do this in a way that minimizes the total white space. Okay. So we kind of have a recursive subproblem that we want to solve, so let's write it out. So let's call it minimize line space of I. This is going to be the total slop of the best line space breakup for words I through N. So we just have words I through N left to decide on, and our goal is to pick a line space to optimize the remainder of the paragraph. So basically, for the rest of the class, we're always going to be using the index formulation. We're not going to really do the previous direct formulations. Okay. So one more thing we need to know is that the definition of slop doesn't care about the last line. So for the last line, like just think of this paragraph, it's not spreading it out so that it hits the left and right margin. The last sentence is allowed to have empty space on the end. So that's going to be important for the base case. So let's solve this recursively. So we already have our decision procedure. We're going to try to find the next line. So how should we do that? What's a clever way to find the next line? So the answer is that's the wrong question to ask. Remember, we never want to be clever. The question is, what's the easiest way to find the next line? What's the answer to that question? You're almost there. What's the simplest thing you could do? Try them all. That's right. Okay. So we should just try them all. We don't have to be clever. We don't have to think about, trying to do something greedy like pick as many words as possible. We're just going to try all of them indiscriminately. and directly pick the best one. So we're going to try all possible line breaks. Roughly. So we still have to make sure the words fit on a line. That's the only caveat. So if they fit. Okay. So let's define this thing. So our base case is going to be when we have no words left or one word left. So let's just say I is greater than n. So we've ran out of words. What's the best slop we can get if there are no words? 0. So if there are no words, we don't have to do anything. There is 0 slop. There is no book. The book does not exist. Easy. We can maximize or minimize the slop on our book by not printing it. Cool. Okay, so otherwise, we have some words. We're going to try all possible options to find the best word. So we're going to have a min over all possible ending words. And this is going to be a greater than or equal to because maybe we just want wi on its own word. So maybe we have a gigantic word like here where we have to put it on just one line. So that's something we want to allow. So we're going to minimize over all j where the total sum of the lengths from k equals I to j of lk is at most L. So this just says we can fit them all on the line. Of course, if we can't fit them all in one line, then it doesn't really matter how much white space there is. Okay? So technically, we also need to add in j minus I, because this is the number of white spaces we'll put on the line between each word. So for our sentence to fit on a single line, we need to care about both the words themselves and the spaces between them. That will take up the total length of the sentence. And you'll notice that j minus I appears in the definition of slop too. Okay. So we have this gigantic min. Now, what's going to be what we're minimizing? So if we put all the words from I to j on the current line, we incur a total slop for words I through j. So let's just make a new function for that, slop ij. And then we also incur slop for everything that comes after. So we also have slop for the subproblem of the remaining words. Okay? Does this look correct so far? It's not. So this is correct if we're not on the last line. So we need one more case, which says if we can fit them all, so this is in j, this will be n because it's all the other ones. So this whole thing can fit on the line, then we'll always do that. And when we get no badness for the last line, we just don't care about the spaces. So if we can fit them all into the last line, we'll always do that. That's clear. There's no reason not to. Otherwise, we have to try all possibilities for the next line break. And we just directly compute those and have the recursion fairy take care of the remainder. Okay? So, one key detail here is how do we compute slop of ij, and how do we compute that sum efficiently? So what's the definition of slop ij? Slop ij. This is going to be L minus j plus I minus the sum of the lengths cubed. Now the issue with these sums is we have a min already. So that's going to add an O of n to our running time. Now if for every single j we're also using O of n to compute a sum of things, we're getting like an O of n cubed algorithm, which is not necessary. We can beat that. So we want to be clever about how we're computing the sums. So you don't have to literally use dynamic programming in advance, but you could. So let's just do that. So we can use dp to compute this thing. Or we can just compute it directly, but in a special way. So the special way I'm referring to is we need to break up the sum. So the sum's the hard part. The sum's the hard part. So how do we compute a sum efficiently? Well, what's a recursive definition of a sum? It's going to be the first element plus the rest. Okay? And then if we want a base case, we could say if I is greater than j, so this is if I is most j, if I is greater than j, then it's the empty sum, so it's 0. So we can also recursively define this sum. So you might be asking why it's recursive. Well, because this is I plus 1. So if we rewrite this to be sum of ij, then this is going to be sum of I plus 1j. So we're always increasing the I. So we get another recursive problem we can solve. So now if we compute this in advance, we use dp to memoize this, throw it in some array, some slop array, then we can compute this in constant time after already computed. Okay? So that's a little subtle point you want to consider when you're doing DP, is there a way to improve what you're doing at each step of the recursion? And if you can, you're going to get a better running time overall. So any questions on the algorithm? The final step is going to be just return the min line space of 1, because that gives us the min line space for all the words. So any questions? Yes. Yeah, so to compute this, we have two indices, I and j. Each one is between 1 and n, roughly. So you have O of n values for each of these. So you have O of n squared subproblems. Each one is going to be constant time, assuming we've already computed the sum. So it's O of n squared. Now the recursion for the sum, it's the same thing. We have n squared parameters, and all we do is a single summation. We just do the 1 plus the recursion fairies result plus just the first thing. And so that's also constant for each pair. So this part's also O of n squared. So in total, to compute slop, it's going to be O of n squared. We do that in advance. And so once we get to this step, it's essentially constant with respect to that function. And just a spoiler, the runtime of the overall function is also going to be n squared. And so that's the benefit of doing this in advance. Otherwise, it would have been n cubed. Okay? But we'll talk more about the runtime in a second. But if there's no questions about what the algorithm's doing, let's talk about that optimal substructure. So the optimal substructure essentially gives us the proof because it tells us induction is something we can use to prove things. So let's look at the picture here. So the optimal substructure for this problem says that we don't have to care about what happened here. After we've chosen those line breaks, they no longer affect the future of the process. And using the same reasoning, after we've picked this line break, then the optimal thing for the recursion fairy to do does not depend on that line break either. So if the recursion fairy optimizes the rest, and we take that solution, glue it to our solution, the whole thing is optimal. Now again, you could think of it by contradiction. Suppose there was a better overall optimal that did not use the optimal thing the recursion fairy did. So maybe the recursion fairy had badness like 5 or slop 5, but there was something else that had 7 slop, and somehow when you glued the 7 slop with the first line we made, overall it had better slop. But why isn't this true? It's because the slops are adding. It's something you add up. So the slop for the previous line is added to the slop of the other ones. So if this had slop like 2, well, the total slop is going to be 5 plus 2 in the first case, and it's going to be 7 plus 2 in the second case. So no matter what happens in our section, the green section we're deciding, it's always better to pick the smaller slop for the future. It never benefits us to sacrifice in the later part. And formally, the reason is because these two sections are independent. The remainder of the paragraph just does not care about where we previously put line breaks. All it cares about is the current word. So the current word, I, is summarizing all that past information, and so we don't really have to worry about it. So contrast that to the n-queens problem. In n-queens, we had to remember everything, because everything depends on the previous stuff. So you can't do dp on n-queens. So in contrast, n-queens have to remember everything. So in other words, it has dependencies. There's past dependencies. Okay? So it's really the same thing as the shortest path in the graph again. To get the best line breaks overall, we need to pick the best first line break, and then the best first line break plus the best remaining line breaks give us in total the best line breaks for the whole thing. So any questions on why this is true? Yes.
I don't quite understand, like, so the seventh slot, would that be a new line, or would that be kind of like existing line?
That's a solution to the rest of the paragraph.
Okay.
So any choices of line breaks in this area, for any of them, we just picked a specific one. To compare it to what the recursion fairy did. So the recursion fairy says, okay, you decided to stop at word J. Now I'm going to pick line breaks for the rest of the words. And the final solution is you're gluing those two together. You're taking your line break plus her line breaks, and you're handing that to whoever asked you to do this process, to the book publisher. But maybe there's someone else who says, hey, I have this solution that has 7 slop. Why don't you use mine instead for your algorithm? But the reason you don't want to do that is because the total slop will be worse. The slop for the entire thing is a sum of 2 independent pieces. So you can separately optimize both pieces. So I guess one optimization way to say this is the min of x plus y is equal to the min of x plus the min of y. That's basically what I'm saying. You can separately optimize both pieces.
Don't those words have to go somewhere though? Like if you make fewer words on one line, then you just send the words to another line. So how are they independent?
So there's slight dependence, but all you need to know is the next word. So the recursion fairy only cares what J is. It doesn't have to know anything else. It doesn't have to know like all the past line breaks, for example. All that information is summarized in just the single word wj plus 1. That tells it everything it needs to know about the past. Yes?
Are you going one line at a time or one word at a time?
One line, yeah. So we're starting at wi, and we're saying what's the last word on the line that starts with wi. So visually, you could imagine you have word I is here, and you're just adding more words to the line one by one until you eventually go over. So maybe this is wj, this is wj plus 1, and then wj plus 2 would be too long. So you have all these possibilities to go on the line with wi, and you just try which ones lead to a total optimal solution. And so maybe you don't want to include wj plus 1 on this line, even though you could fit it physically, because that results in something bad in the future lines. So that's what the process looks like. Yes?
Are we taking the longest word possible that starts with
No, that's a greedy algorithm. We're not doing that. We're trying all possibilities. Brute force. What's the last thing that goes on this line? I don't know. Try them all. So we just try each one individually and see what happens. Yes?
If the picture you've drawn already is not the dependency diagram, can you draw the dependency diagram?
Yes. So I just wanted, so this is basically the proof of correctness. So if you have optimal substructure, then induction directly gives you the proof. So really all you have to argue is the optimal substructure part, which is usually why DP algorithms are super easy to prove, because it's just like, we tried them all, and optimal substructure. Okay, so now we have to do the DP stuff. So let's just focus on the total MLS algorithm. The same ideas apply to slop. So how many subproblems do we have? We have a subproblem for each I. So what values can I take? swap that minus for a plus. So you have one subproblem per I, and I can be anything from 1 to n plus 1. Again, it's n plus 1 because we might run out of words. So that's that case. We might not ever hit that base case, but just to be safe, throw in the n plus 1. Okay. So what's the data structure we want to use? What's something that can store n plus 1 things in order? An array. So we have an array 1 through n plus 1. And now we have to do the dependencies, which is the main part. So we have our array. So what does I depend on? Just like in LIS, it's going to depend on every single thing to the right. So it depends on I plus 1, I plus 2, all of them, up to n. Okay? So what's a good evaluation order? Well, we're going to evaluate it like this. So it's going to be a loop that starts at n and goes up to 1. Or down to 1, depending on how you want to phrase that. Okay? And the last step is going to be the running time and space complexity. Well, the space for the entire algorithm is going to be n squared because we have to save all the slop values, but for just this part, it's O of n because the array is 1 through n plus 1. The running time is going to be O of n squared. Now, this is because we have O of n subproblems, but remember, we have a for loop to do the min. So this is per subproblem. And this is number of subproblems. Okay? So then for the overall algorithm, we're going to have space of n squared. The n squared dominates the n array. This is for slop, saving all the slop values. And the total time is still going to be n squared because it's n squared plus n squared. Okay? Yes. It's j plus 1 because j is the last word. I is the first word on our line, and we're choosing j to be the last word. So if j is the last word, then the next word on the next line is going to be j plus 1. Yep, good question. Any other questions? Yes.
My question might sound a little bit absurd. So would it be possible if we just said like I is greater than or equal to n, and that would be kind of like the last word on that line instead of writing?
Yeah, totally. I just do it that way just to be consistent. But absolutely, you can use a greater than or equal in the base case. Yeah, almost all the time you can simplify or tweak these algorithms slightly to be more efficient. I'm just making it as simple as possible. Yes?
Do you store the unchosen but explored branches? I don't know if that's a clear way to
Yeah, so there's slop values, slop ij, that will never actually be used. Because, for example, certain pairs just are less likely to be useful. But we're going to compute all of them.
So if there exist many decisions for each word, why do you only need to store a single value for each word?
Because you can summarize by just the line break or just the total slop. They're equivalent. So for I, you're just deciding, what we're actually doing is deciding where's the line break for the line containing I. That's just a single value. Or think of it as you're just saving the optimal slop value for I, which is what we're actually doing.
Okay. So at each stage, the min part compresses them all to that one value.
Yep.
Which is then stored.
Yep. Yeah, so the thing we're computing, the solution is going to be the j value, and then the actual thing the recurrence is computing is the total slop, the optimal slop value. So remember, you can usually compute numerical values like total white space or length of your sequence, and you can always convert that into an algorithm that computes the actual solutions. Because all you'd have to do is return j every time you do this. And then you get both. So I'll just say that. Add a return argument to get actual solution. Okay. Any other questions before we go to 1,000 times harder problems? Especially if the optimal substructure is a little confusing, let me know, because we're going to use this literally every time. Yes?
Why is this substructure optimal?
So optimal substructure says for a given breakup of your optimization problem, that gluing each individual piece of the breakup together gives you the overall optimal. So your overall optimal solution are optimal pieces glued together. So it's saying you're taking the optimal line for I, gluing it to the optimal line breaks for everything else, and those together give you the optimal for the whole thing. And so that's the min x plus y thing. It comes from the fact that the minimum total slop is just the min slop for the first part plus the min slop for the second part. Yes? No. This is the reason. So if you took any number here that was different from the optimal for the rest, your total slop is not better. So if 2 is the best slop for just i's part, and then you add that to 2 different values here, well, you're just adding them, right? So adding something bad with something good will still be worse than adding something good with something good. Like 7 plus 2 is 9, 5 plus 2 is 7. No matter what you put here, the smaller one will always be the better one.
So this is the case where we're saying in the case where there is a line break here, take the optimal.
Yeah, exactly.
Because we know it's fixed that there's line break here.
Right.
How is that not the greedy one though? Because if you're optimizing each little section or whatever, aren't you just doing some sort of greedy something on each of the sections?
but we're optimizing over the entire process. That's why it's not greedy. So greedy are locally optimal. So a greedy algorithm would say, pick the word that optimizes something right now. So right now, we don't see the future words. We only see this line. So we're just trying to minimize the line, the badness, the slop of this line only, without thinking about the future lines.
And how is thinking about the future lines in the problem? Where does that show up?
That's the recursive part. So the min takes into account the future slop too, not just the current slop. So it's the current slop plus the future slop, which is the overall slop for this particular choice of line breaks. So that's kind of the min x plus y thing. It's saying total slop equals current line slop plus future lines slop. And just an artifact of our objective function being a sum of things. Just by the definition of total slop, it's the sum of the slops of each line. And so you can compute that recursively by saying the first line plus everything else by induction. Any other questions? Okay. So the next problem we're going to look at is trying to balance parentheses, which if you've ever programmed is super annoying, but now DP can do it for us. Yay. So here's a recursive definition of what it means for a string of parentheses to be balanced. So either W is the empty string, it's just nothing. Nope. We'll use epsilon to denote that it's nothing. So obviously if you have no characters, it's vacuously balanced. Otherwise, it's two matching parens, or matching brackets, with something else that's balanced inside of them, or it's two balanced things concatenated. So this one's concatenation. So, for example, this would be a balanced string. So that's just a recursive definition of what intuitively we'd think of as balanced strings with parentheses. And you can prove this one's balanced by breaking it up into pieces. So the first piece, x is balanced, the second piece, y is balanced, and then recursively you figure out if those are balanced, etc. Okay? So any questions on what balanced strings are? Cool. So the first thing we want to do is we're given a string and we want to figure out, is it balanced? So, is balanced. Now what's really handy here is we already have a recursive definition of what it means to be balanced. So we can just plug that into recursion and get an algorithm instantly. So that's nice. But we want to DP-ify it. So we need some kind of index formulation. So let's define isBal ij to be true if and only if our input string, the subsection ai through j, is balanced. So maybe this would be 1 through 10. So if we plug that into is balanced, we should get true because we know x is balanced. But if we just put in the last character, so if we put in nn, we should get false because a single paren is never balanced. So that's what we want to compute. So let's just write out the recursive definition. So our base case is awesome. It just says if I is greater than j, then true. The empty string is balanced. If I is equal to j, we have a single character. It's always false. You have to have at least an even number of things to be balanced. So otherwise, we have I is less than j. So if I is less than j, we have, let me say it's significantly less than j. Now we have a bunch of characters we have to think about. So it's balanced if it satisfies one of these cases. So there's two cases. First, we have the matching case. If the left and the right ends are matching, we're done. So let's just say if AI does not match with AJ, so this means does not match. Really, it's an if statement, right? You're checking if AI is a left paren, then AJ is a right paren. Otherwise, if AI is a left bracket, then AJ is a right bracket. Yes.
Why is I equals j false?
Because that means you have a single character.
But isn't that fine? You could have like the letter A and then the empty string.
No. This is the definition of balanced string. If you had just a single character, that means you have a left paren or a left bracket, and it has no matching right paren or right bracket. Like a single left paren is not matching.
But you could have like down there the last one is xy for some balanced strings. Oh wait, never mind, because there's only
Right. So the issue with using the last case is that a left paren doesn't satisfy the other cases. But you should just use your intuitive understanding what balancing is. You don't have to worry too much about the recursive def. If your program compiles, it was balanced. Yes?
Why I can be bigger than j?
You mean in this?
Oh, so
This is just saying, yeah. So if you plugged in a pair of I and j where j was smaller than I, well, you can't have an array from 5 to 3. That's empty. Okay? So if AI and AJ do not match, well, we can't use these two cases. So these two cases are out. So our only choice is to use the last case. So we need to break up our string into two substrings. So how do we break it into two substrings? There's a 3-word sentence I'm looking for. Try them all, yes. Cool. So we're just going to have an OR over all possible k from I to j of is balanced I to k and is balanced k to, or k plus 1 to j. Okay? So we're going to try every possible last character in the first string to define the two component strings. So ultimately, we're trying all possible substrings that go right next to each other. And then just according to the definition, we need both of them, x and y, to be balanced, so we're going to recurse on both sides. Okay. Now, if AI does match AJ, we have more options. So if AI matches AJ, we can do the same thing again if we want to. So this is an option. Or we could use one of the previous definitions. So the other option is we essentially pick off the left and the right part and then recurse on the middle part. So in this case, we want to check is balanced I plus 1, j minus 1, because we're ignoring these two. And we're just recursing on the middle string x. Okay? So either it's some balance x followed by some balance y, which is the first case, or we can remove those two parens and then recurse on the middle part. And if either of those cases are true, then by definition of a balanced string, it's a balanced string. Okay? And at the very end, we're going to return is balanced on 1 and n. That way we get the whole array. Any questions on this algorithm? Yes?
Can you just explain the case where AI and AJ do not match, like what's going on?
Yeah. So this is implementing this part of the recursive definition. So if there's no matching left and right paren, we can't use the top two cases. So our only option is for that to be true. So how are we going to actually check this condition? Well, we need to try all possible x, y pairs that build into W. So how do we actually construct x, y pairs that are equal when concatenated to W? Well, W for us is I through J. So let me actually draw this. Draw a little array. So this is I through J. So if we want to break up I through J into two things, x and y, we can try all possible last things to define that split. So k is defining that vertical line. So we pick k, everything between I and k becomes x, everything from k plus 1 to y k plus 1 to j becomes y. And we're trying all possible k's, and so we're going to get all possible xy's. Other questions? Yes?
Why do you have an or on the case you wrote in orange if there's only one representative?
We're oring that with the previous one. I just didn't want to write it out again.
Oh, okay.
Yeah. Because it's balanced if either it can be xy or if it's the middle part's balanced. Either of those is valid. Yes.
What is that saying in English? Sorry, I'm lost.
It's saying in English this definition. So it's saying the giant or is saying You can break it up into an XY where both are balanced.
Okay, so then we start slicing it at random halves until we find the right one.
Yeah. Or maybe you can't do that. Instead, you have to take a left paren and a right paren and sandwich something that's also balanced in the middle. So that's the other thing. Why does it keep doing that? Go back. So that's this case. This is the middle thing. So this is saying we took a left paren, so W equals a left paren, X, and a right paren, and this checks that X is balanced.
Okay.
This part is checking that W has a left and right paren.
So wouldn't that be balanced then in the orange case, but not balanced in the black case?
It's balanced if the smaller X in the middle is also balanced.
Oh, okay, we're checking that the whole thing is balanced, not that the outermost part of it.
Yeah, yeah. Yes.
I just want to know, is K or is random number behind I? How do you choose?
No, we're trying all possible K. Yeah. So this OR here, the OR goes from K equals I to J. So it's really a for loop over all possible K, right? Because we're always trying them all. Yeah. Other questions? Okay, so what's the running time? You should be able to tell me without knowing anything else. Close, it's n cubed. So there's n squared subproblems, but we have the giant OR in the middle. So for each subproblem, we're going to have a for loop that takes n time in the worst case. So the running time is O of n cubed. So we have O of n squared subproblems and O of n per subproblem. How much space is it going to take? We have to save every subproblem, right? How much space do we need to save n squared subproblems? N squared. Cool. Now, what's the dependency graph? Obviously, we want to use an array. That part's easy. That's our data structure. I'm going through these faster because they're kind of mechanical. The main part's the graph. So what's our graph look like? This thing's a monster. So let's say I is the rows. This thing goes from 1 to n plus 1. And technically it doesn't, so let's be precise. This actually just goes to n. This one actually starts at 1. You'll never fall over because of the I equals j base case. This is j. This goes from 1 to n2. And now we're in the middle. It's some ij. Now, what does ij depend on? It's not so easy as the other ones. So just give me one subproblem it depends on, the easy one that is highlighted. I plus 1, j minus 1. So let's throw that one on first. So I plus 1's the next row, j minus 1's the previous column. So it's going to be right here. So we know this one has a dependency. Now what about the big OR? So the big OR, let's look at the first part. So we have ik for all possible values of k bigger than I. So we're on the same row as I, but the k values are going to be bigger than I, right? Yeah, the k values are bigger than I. So we're in the same row, but the column is going to be, I think, to the left. Same row, different column. So, okay, yeah, so it's going to look like this. So this is ik for k less than I, or k greater than I. Oh wait, that's reversed. These are all going to be over here. Yeah, that looks right. Okay, cool. Okay. The other one is k plus 1j. So k plus 1 goes, it's going to be down here, down there, and then it's j, so it's the same column. So it's going to look like this. So this is k plus 1j, and that one's, let me write it over there now. This one's ik. And technically it's going to look like, it'll be like a diagonal thing, like a triangle, if we kept spreading it down. And all of these have dependencies. Every single one. So what's an order that would work here? Well, the key thing to notice is that the I dependency is really important. So we definitely need an outer for loop that goes up, for sure. But the k dependency actually doesn't matter. It really doesn't matter if we go left or right. All that matters is if we've done the like lower part of the matrix first. So I'm just going to put a double arrow to denote the fact that it doesn't matter. If you prefer to be concrete, pick one. Whatever you prefer. If you like j going up, if you like j going down, really doesn't matter. Okay, so that's what our graph looks like. And so if we had to pick the eval order, it would be for I is n down to 1, and then for j, I'm just going to pick one at random to n, but this can be whatever you want. Any order. Could be a weird order. We don't care. I just picked one. So that's going to be the eval order. That's pretty much it. So this is just to show you that sometimes the picture can get really complicated, which you'll see if you do the edit distance, if you look at the chapter about edit distance. Yes?
Are there any cases where we wouldn't want to use either 1D or 2D array as the data structure?
For this particular problem?
Just, I guess for like kind of any, just because it seems like we've done like explicitly like that. Unless I'm
We've used 1D arrays in the previous problem.
Yeah, I'm saying, like, is there any case where we wouldn't use 1D or 2D arrays?
Like 3D?
Or just
We're going to use 3D in the next problem, if that gets you excited.
I guess, like, anything that's not, like, an array.
Yeah, so do you remember, so on Monday's lecture, we did the maximum independent set problem. And in there, the memoization structure was a tree. and we did a post-order traversal of that. And we'll do another tree problem today too.
So is that like,
So to answer your question, this data structure could be anything. It's just whatever matches the problem you're working on. So this thing could be like a Fibonacci heap if you're doing a really hard problem. It could be some very strange data structure like a disjoint union. It could be any data structure. We've just mostly been doing arrays because the problems themselves we were trying to solve were array problems.
so if we're like working in like a tree, should we just use a tree?
Usually, yeah. It's a good rule of thumb. Usually the data structure will match the type of problem you're trying to solve. Okay, so that's just for is balanced. Now I claim you can immediately convert this into an algorithm to find the max length balanced substring. So remember, a substring means it's continuous. So it's something like AI through J. A subsequence can skip things. So this, you cannot skip things. So how can I find in my array the subarray of longest length that is balanced? And we're going to reduce it to is balanced. So you have is balanced that you can use for free. So how could you compute this? Yes, we're going to try them all. Here's the algorithm in one line. Return the max of all I less than or equal to j of isbal ij times the length, which is j minus I plus 1. So what is this doing? Essentially, we're checking for every possible substring. Is it balanced? And if it is balanced, then what is the length? So if it's balanced, that will be a 1. The thing in brackets will be a 1. So we get 1 times its length. If it's not balanced, it'll be a 0, and we don't consider it. So this immediately tells you the substring inside the array that's balanced of max length. And we had to do absolutely nothing. So this is going to be n squared because we do an n squared search plus O of n squared to compute is balanced. So this is for the max. This is for computing is balanced. Okay? So again, an example where we started with an easier problem, which is just checking is it balanced. And then we got immediately for free a way harder problem, which is finding the longest balanced substring. So any questions on how we just immediately extended it? And notice this is a reduction. We're reducing to the is balanced problem. For the sake of argument, you're pretending is balanced was given to you. Don't think of the fact that you yourself made it. You can just assume it's correct and then plug it into this one line to get the correct answer. So this whole algorithm is correct, assuming is balanced is correct. And that's why it's a reduction. Just want to emphasize that again because reductions are so important in this course. You always get to assume something is correct. You're black boxing it. You're pretending it's magic, someone gave it to you, and you can use it however you want.
Is that just valid because of something like conditional introduction or whatever?
Yes.
Is that basically what it is?
Yeah. So we're assuming his balance is correct, assuming that this is correct, and then separately we proved his balance works. So the whole thing works. Okay. So So you can also extend this to work with subsequences. So that's part B, is subsequence, not substring. Substring is actually harder, so it's kind of funny that we did it in one line. So for subsequence, it's almost the same thing, but instead of using ors, you're going to use sums, essentially. So if you want the longest length, then you either get the length plus the length here. So this will become a length, this will become a length, this is a plus, this is a max. Or you get 2 plus the length there, because you had 2, a left and a right, and then you have the inner thing. So just by tweaking this, we also get the longest subsequence too. So I'll leave that as an exercise if it's not immediately clear. So any questions so far? Yes? It might be. Yeah, it is. Sorry. Yeah, you're right. Yeah. Is balance is n cubed, so this whole thing's n cubed. Thank you. Cool. Yes. Yes, thank you. Okay. So what's the optimal substructure here? Well, it's okay. Optimal substructure is not the right word for is balance because you're not optimizing. It's just a true or false. So the equivalent would be why inductively is it true? And that's just because we applied the definition. So this one's proof is actually easier because it's directly by definition. Now if you can look at the length version, so the longest length balanced, where you put a max and sums, then it comes from the fact that the longest thing you can have, so let's say you had a left paren, x a right paren, its length is 2 plus the longest in x for this first case. Now, if the recursion fairy tells you this answer is 5, but someone else gave you an answer that was 3, there's no benefit to you taking the 3 over the 5, because the total solution length is going to be 2 plus that number. So again, we have a min x plus y, and so, well, actually here it's a max. So this is the max of x plus the max of y. So the optimal substructure just comes from the fact that you don't benefit from shrinking the result for the subproblem. 2 plus 5 will always beat 2 plus 3. It does not help you to sacrifice in the smaller region. Does that make sense? I can draw more pictures. Yes.
Oh, yeah. Can you draw more pictures?
Yes, yes. Okay. So let's just say this is the whole array. This is a left parenthesis, this is a right parenthesis, and the rest is called x. So let me tell you, I'm just going to promise you, as an almighty person who knows this problem perfectly, that you should include the parens. I'm going to give you that for free. So if you know, you should include those parens in the longest thing. New page. So if you knew that, then the total length you get of your subsequence is going to be 2, because you have one left, one right, plus something in x. That's the total length of your subsequence. So your subsequence is going to be a left parenthesis, a right parenthesis, and something in the middle. Now, would it benefit you to pick something less than the best thing for the middle? So if I told you the best thing for the middle was 7, but you wanted to use something of length 5, well, what's the total length going to be? It's going to be 2 plus 7 versus 2 plus 5. So the idea here is you don't benefit from taking a suboptimal solution in the smaller area. So let me give you a specific example. So let's say we had a left-right and a left-right. So the entire thing is actually balanced. So what's the longest thing going to be? The whole thing, right? So the whole thing is balanced. So the optimal is going to be 6. Make sense? Can't have anything longer than everything you have. And notice that these are also optimal for the subproblem. So what's the longest balanced substring of just the inner region? 4. We take everything again. So the optimal thing is also 2 plus the optimal for the middle. Now, if instead I said, well, maybe we shouldn't do the optimal thing in the middle, let's just take these two. What's the size of your solution? Yep, so now you have 2 plus 2, which is 4 instead of 6. So it's worse. That's what optimal substructure says. You don't benefit from not taking the optimal thing in the smaller regions.
And if you would benefit from that, then it is a dynamic programming problem?
It still could be, but you have to, the proof would be different. Most of the ones you'll see have optimal substructure. Usually, if it's not the case, then there's extra dependencies, like for n queens. And so it'd be a backtracking algorithm, but not dynamic programming, usually. But I don't think I'll give you anything like that. But good question. Does this picture clarify a little bit? Yes.
How do we determine like the optimal for the middle?
By recursion. The recursion fairy does it. Remember, it's a smaller region. Recursion fairy can always handle smaller things. You don't have to worry about it. So the idea here, the reason optimal substructure is important is because it allows us to use induction. So we know the recursion fairy gives us the best thing here, but we don't really care if that doesn't help us. Optimal substructure says the best thing in the middle helps us. So the recursion fairy gives optimal in the smaller region, but that's useless without the optimal substructure. Optimal substructure says what the recursion fairy is doing helps us. Any other questions? Again, when you're in doubt, just think of the shortest path example. You would never drive down a road that was longer if it didn't overall benefit you. Okay. I'm going to skip that. That's in the textbook. Okay, this is the important one. So now you're playing a game on a n by n board. The way this game works is you have a stone, and you're going to drop your stone anywhere you want. Then, after you've dropped your stone down, you can either move it down or to the right. And you can keep doing that until you fall off the board. So eventually you fall off the board and the game is over. So you can move down or you can move right. Now, every single spot you hit, you gain a reward that is equal to what's on the cell. So for this example, your total reward or your total payoff for the game is this. Because you're on 8, and then you move to -6, then to +7, etc. And that's the number of points you get. Of course, your goal is to maximize your points. Okay. Any questions on the game? Yep. And when you fall off the board, the game's over. You can fall off the board to the right or down, either one. The only thing that's different is you can put the initial stone wherever. So if you wanted to, you could start by just putting your stone here. And then you would immediately drop off if you wanted to and get 7. Okay? So there's 2 things you get to pick. You get to pick the initial spot, and you get to pick, once you're at a spot, whether to move down or move right. So that's the entire game. Yes?
But if I place it on F7, fifth row, can I move to 1 on the right?
Yeah, if you want to, you can.
Okay, so the game is over if I move the stone out of this board.
Yes, yeah. So you can move it all the way to the right off the board or all the way down off the board. Either one's fine. Okay, so we need to solve this problem. Is there a picture? No, that's the only picture. Okay. So like usual, we want to pretend we're in the middle of this process. So picking the initial spot, we only do 1 time, so we can ignore that for now. Let's just focus on the downs and the rights. So what's a good summary? What's important information we need to know to determine whether we should go down or right? What do we need to know?
The values that we lose out on by taking the options.
Even simpler.
What the next value is.
Even simpler.
Current values.
Basically. So where are we on the board? That's what we need to always remember. This will define our subproblems. So let's define max score of ij to be the max score we can get if start at aij. So that's the problem we want to solve. And then let's say we've solved this problem. Then how do we solve the overall problem? Not the sums. Yes.
Take the max over the set of all AIJs.
Yep. So in other words, this is how we pick the initial spot. So we're going to return the max over all ij of MSIJ. In other words, pick best initial spot. So ultimately, that's what we'll do at the end. Now we have to recursively figure out what to do when we're in the middle of the game. So the nice thing here, again, if I told you we're at the position with an 8, you don't really care about what happened previously. It doesn't matter whether your score in the past was 100 or whether it was negative 50. All you care about is maximizing your score from now to the rest of the time. So that's the optimal substructure. Here I think it's even clearer. Why would you ever want to take a smaller score? It doesn't really help you overall. If your previous scores were 100 and now you score a 40, but you could have scored a 50, you're still getting a better overall score if your ending part is 50 instead of 40. So we would never want to do anything less than optimize over the submatrix. You could think of this for like any sport too. If you have 100 points in basketball right now, and I told you you can get 40 more points, there's no reason to not get 40 more points. It's not going to make you lose to get 40 more instead of 30 more. It'll only make you win even harder. So that's the optimal structure. Okay. So using that substructure, we can try to recursively solve the problem. So, what decisions do we need to make? Down or right? How do we make them? We try both, yes. So we're going to do a max of 2 options. So the first one is if we move, well, before we even do that actually, we're at the current cell, so we're going to get the current payoff. So if we started at the cell with an 8, we get an 8 immediately. So that's why we're adding the AIJ. Now we have to decide the next move, and the next move is going to be either we move to the right, which means we increase the column, so J is increased, or we go down, so we increase the row, so I is increased. Is there any other options? That's going to be taken care of inductively. So that's going to be our base cases.
Are you not asking for more?
Just for this part, just for this line. Is there anything else we need to add to this line? Yes.
I think like maybe we can go purposely off the board because what if the right and the downside is negative numbers? So that's
Then you can go.
I cannot go.
Yeah, you can. So you're going to move right or left. If that happens to be off the board, then the base cases will take care of that. But is there anything else we need to add just to this line? Ignoring base case stuff, like going off the board. You can say no. It's okay to say no. You can be confident.
This line as in the last section.
Yeah. You're right. So we tried going down, we tried going right. There's nothing else we can do. So that's it. So now we have to think about the base cases. So one base case is if we fall off the bottom of the board. So that's when I is greater than n. If I is greater than n, what's the total score of the empty board? 0. If we fall off the right side of the board, that means j was greater than n, and again we get 0. So that's the entire thing. Solving this whole game, just this tiny little recurrence. Any questions on the recurrence? We can go down or we can go right. We tried them all. And then we tried all possible starting positions. So of course it's correct. So now let's analyze it. How many subproblems? Just say any number, but say it confidently.
3.
Yes, n squared. So that's the subproblems. How can we save all the subproblems in an array? 1 to n plus 1, 1 to n plus 1. Cool. That's our data structure. Now we get to draw a picture. That's the best part. Okay. We have I.
What are the indexes of the array and that how it goes from 1 to n plus 1 and oh it's 2D. Sorry.
Yep, it's 2D. So we have some square, ij. What does ij depend on? Hint, the picture will look like the game.
Left and the right. Or is it left and the down or right and the down?
Yes, down and right. So I plus 1j and ij plus 1. That's it, just 2. So what's a good eval order? I mean, there's tons of eval orders. You could do it like diagonally if you want. That works. If you look at Jeff's notes on edit distance, you'll see literally all of them. It's kind of impressive. But let's just do an easy one. So we'll do, so the double arrow denotes the outer loop. So we're going to do I from n up, and we'll do j also from n up. So we'll get 2 for loops. And then you slap your recurrence in there. So what's the running time and space complexity? Well, we're just taking a max and doing an add of only 2 things. So O of n squared, because n squared subproblems, times O of 1. And then the space is also O of n squared, because we have a 2D array, each one having entries up to n and up to n. That's it. Any questions on the DP stuff? Hoping it's starting to become very mechanical. This is literally all you'd have to write for the homework. Yes?
About like evaluation words, so like, I know this one we use kind of like going like backtracking, if I understand correctly.
Mm-hmm.
But how do we determine the evaluation orders?
We determine it so that ij is processed after the things it depends on. So in particular, for ij to be processed, we need everything in the previous column, or everything in the next row has to be processed first. That way we know I plus 1j is available for us to use. And we also need everything in the previous columns to be ready for us. That way ij plus 1 is ready when ij needs it. So if you compute in this specific order of I and j, the green arrow indicates I plus 1j is computed before ij, and the purple arrow indicates that ij plus 1 will be computed before ij. And this is just a pictorial representation of these loops. The I loop is literally the green arrow, just written in pseudocode, and the j loop is literally the purple arrow. And so if you use this order, you'll always have those child subproblems computed before ij is computed. Other questions? So there's another version of the game. It's significantly harder, but it's so fun. So we're going to do it. So in the European version of the game, you can move left, but you can never have the same cell touched twice. Otherwise, you get an infinite loop, which is a problem. So if we go back to the picture, you now have the option to move to -9 if you wanted to. But if you do move to -9, you can't move back to 8. You're kind of stuck at -9. And then you can either go to -4 or go down. You can't move right again. No, you can't move up. Never. The game would never end if you moved up. In fact, if you allow it to move up, it becomes MP complete. So, impossible to solve. Yes?
Does that imply now that we can fall off the left side of the board?
Yep. That's a valid option. So this one's a little harder to solve.
Can we re-enter the board from off the board?
No. Once you're off the board, you're gone forever. You fall into the void. So there's two ways to solve this. The key observation that will make this possible. If you move left, the next move can't be right. So you can only go down or left. So in particular, if you move left, now you're going to get basically the same game originally, but just with a left arrow instead of a right arrow. So it's almost the original game. So the hint here is we should keep track of whether we moved left or not. That's an additional thing we want to keep track of. So there's two options. We can either explicitly have a parameter that's like left or not left, or we can just have two functions. So the left or not left version is kind of similar to the maximum independent set thing we did. So let's look at the dual function version. So we'll have two functions. So what should we call it? Okay, so let's call the first one max score. You always want to use, names that are symbolizing something. So this is going to be max score of ij. This is the max score of the European version of the game, starting at aij. And now we can either put an L here to symbolize whether we took a left or not, or we can make a whole function, MSL of ij, which is the same thing, assuming last move was a left. And so this one's going to be almost the same recurrence as before, because by definition it's basically the same. We can never go right again. We can only go left or down. So in terms of gameplay, it's basically the same thing. The MS one, though, is a bit more complicated, because in that one we can either move left or move right. So are the definitions of what the functions are trying to compute clear? Anyone want to be bold and say yes or no? Nods are cool too. Okay. So let's start with MSL because it's actually easier. It's going to basically be the same thing from before. I kind of want to just copy the same thing as before, actually. That would be nice. Please let me copy you. Please. Yes. So MSL. So what do we have to change? Well, now we move left. So I greater than n will never happen. I will become less than 1. Nope, it's columns. That's backwards. I still is greater than n. J is going to change. So j being less than 1 means we've jumped off the left side. And now instead of moving to the right, which is ij plus 1, we'll move to the left, which is j minus 1. That's it. Like I said, it's basically the same game, so really easy. Now what about ms? This one's a little chunkier. So we get aij, like normal. Now we can either move left, right, or down. So we can take the max of ooh, I just thought of an even better way to do this. Ooh, it's so risky though. I'm just going to write it like this and we can figure it out later. So this is moving to the right, this is moving to the left, or moving down, and then this one is moving left. So for the left case, we're calling the left function because it behaves differently overall. I see it now. This should be an MSR. So we also have an MSR, which is the MS from before. Oh, that one's down. So MSR is the same one from before. Okay. So what's happening here? So we get our aij. We can go down, which is just ms again, for the next row. If we move right, we can't move left again, because we'll hit the same cell. So we're using ms right, which is the thing we computed in the previous problem. Or we move left, we call MSL to ensure we keep going left. So we use these two different functions to make sure we never end up hitting the same cell again. Once we've committed to right or left, we have to stay going right or left, at least in that row. And then our base cases are the same. So if I is greater than n, if j is greater than n, and if j is less than 1, these are all 0. But really, these two will never actually happen because the role of MS, you could really call it MS down if you wanted to. Its role is just to allow us to go down. It doesn't care about the right and the left because that's the job of the MSR and MSL functions. So this is the entire algorithm. Okay? Now, assuming we've pre-computed MSR and MSL the same way in the previous problem, then the subproblems, well, the running time will be n squared. So there's n squared subproblems just like before. There's no change there. And the amount of work per subproblem is O of 1 because we're just doing an addition and a max of 3 things. Again, we're assuming MSR and MSL are already computed, so those are constant time. The space, again, is O of n squared. Now the diagram's actually easier. So like I said, MS only cares about MS for the previous row. So if we drew the picture here, what we have is I and j. This cell ij only depends on I plus 1j directly. The other dependencies are on completely different charts. So then we have the MSL chart and the MSR chart. Maybe we should make this one R. So then we have other things, and these that it depends on. But we're pre-computing both these matrices completely. So for the purpose of this box, we can just ignore these. These don't matter. Can ignore. So all we really need to do is have I go up in an outer for loop, and j can do whatever it wants. We don't care. J is just doing whatever. Any questions? Yes. It is MSL.
Like the first thing on the
Oh, yeah. This part, yeah, that's an L.
Are they both MSL?
Yep. Let me just... Yeah, so this recursive problem only depends on itself. Because you can only take left moves once you've made a left move.
But if you're doing I plus 1, wouldn't you be able to make a left or a right?
Yes. That is true. So if we go down, we loop back to MS. So in the same row, we have to keep moving left. But once we go down to the next row, we can go left or right. So good catch. Questions? Yes?
So when you get to the next one, you can't go down.
You can always go down.
Okay.
That's the down part.
Okay.
Yeah. So both in MSLL and MSR, you can always go down. And then the full thing MS, you can also go down. Down is always an option. But whether you go left or right depends on what you did in the past. So I'll just say that. So this is another way you could write this with just one function, which I do want to mention. So we could have ms, ij, and last move. So this is max score starting at aij if last move was L. So now we're just going to have if statements to do everything for us. So if the last move was down, we can do whatever we want. So if L is down, then we can do ms. Well, we need a max, of course. So we have ms I j plus 1, and our last move is now our right move. We can do ms I j minus 1, and the last move was a left move. Or we can do I plus 1 j, and the last move was a down. Similarly, if we had L equals left, we'd have aij plus the max of ms I j minus 1 left move, or ms I plus 1 j down move. The last one is if L equals R. It's going to be basically the same thing, but I feel compelled to write it. ms I j plus 1, move right. ms I plus 1, j, move down. And you have your base cases as before. I is greater than n. J is greater than n or less than 1. 0. So this is an alternative way you can do the same thing if you prefer adding a parameter instead of using multiple functions. It's really up to you. Everyone has a different preference. Now the downside to this one is the picture is 3D. But you can usually ignore that because how many values can L take? 3, so it's constant. So what's the number of subproblems? It's 3 times roughly n squared, which is O of n squared. So even though we have 3 input parameters, it's still n squared. It doesn't really impact you much. So the running time of this is still going to be n squared. These two algorithms are equivalent. The space, again, you're using a 3D array now, but one of the entries is just 3 entries. So it's still n squared space too. Now when you're drawing the picture, what I'd recommend you do is have 3 separate pictures. So ultimately, you're going to do the same thing. but the interpretations are different. So you're going to have a chart for ij, but L is equal to down. You'll have one for L is equal to right, one for L equals left. And each of these will depend on separate pictures and the same picture. So you'll get something like this. But again, you can still define an order. And it's even clearer here what the order is, because what you can do, you're still going to have I from n to 1. You'll have j, I believe, in any order, so I'll just do 1 to n. And now you'll also loop L. And the important thing is it doesn't matter which order you do L, R, and D. So in essence, it doesn't matter which chart you're looking at first, as long as you guarantee the previous rows are computed in all of them. So really, we only care about I for all of them. If you know the previous row of the L box is computed, then you can compute the one for the D box too. Even though there's 3 pictures, it still boils down to just make sure the previous rows are computed. And that will be the eval order. So this is an alternative way to do the mutually recursive thing. Both are totally correct, just whichever one you like to think about more. Both of these will be useful for the dance revolution problem and for the solid block problem. So keep that in mind. Yes?
How do we know if we end up with a 1D, a 2D, or a 3D picture?
It's just whatever needs to hold these subproblems. So to hold these subproblems, you'll have an entry in your array for each I, j, and L. So it's going to be 1 through n plus 1, 0 through n plus 1, because j can go over either side, and then L is 1 to 3. So it's a 3D array, but one of the dimensions is kind of small. So instead of a hypercube, it looks more like a brick. Yeah, so that's the way I drew it here. But what I personally like to do, and what I did when I solved this on the homework for Jeff's class, was this. And then you draw little cubes. And these cubes depend on other cubes. There's a bunch of cubes. So you can also do that if you want to impress me with your artistic skills. Oh, don't. You can, but you shouldn't. No, what I usually do is I'll just draw it in like my iPad, screenshot it, and you can include images in LaTeX. That's the easiest way to do it. LaTeX is more of drawing the pretty curly brace stuff. That's what you want to do in LaTeX. Picture is better on paper. And the eval order looks like this, if you're curious. The picture's rough, but I'll upload the actual picture I submitted on my homework if you're curious. But yeah, that's all. Any questions? Yes.
There isn't one like strict validation But the first and foremost is definitely go. It's a backtracking go down.
Yeah, so I has to be from N to 1. J and L, whatever.
So we can
Doesn't
go
matter.
horizontally both way and then back.
Yep, if you prefer, we can make this an N and this a 1. We could, there's other orders that disgust me, but Jeff wrote them in the notes so you can look at them. Like actually. Where is it? I went too far. No, I didn't. Here it is. Here's an example of 3 different orders of the exact same recurrence. All of them are valid. This one is very hard to actually code, though.
Well, if they're optimal among 3.
Nope, they're all equivalent, exactly the same. At the end of the day, you're going to hit all of those entries, just in a different order.
The hardest one looks to produce.
This one? Yeah, it's the most natural order, right? If you're doing diagonal by diagonal, that's kind of what the problem wants you to do. But the actual pseudocode for doing diagonals is kind of annoying, wherever it is. Yeah, this is it. That's how you do diagonals. But if you just do this, it's easier. But for purposes of this class, if you draw that, you can draw that. Like, that's totally a correct answer. But if you're ever trying to code it in actual code, please don't code that. It's very buggy. Other questions?